We have spent some time talking about analysis of variance, which is an extension of t-testing and z-testing. We've talked primarily about a form of analysis of variance, completely randomized analysis of variance, and we took some time to talk about an analysis of variance in which there is more than one independent variable. And we looked at, briefly, the nature of an interaction effect. And what I want to do today is sort of summarize, first of all, summarize issues associated with analysis of variance, and then work through another specific example. I indicated before that ANOVA, analysis of variance, is an extension of t-testing or z-testing. And more specifically, the route that we have taken is to, when we talked about t-testing, we talked only about uncorrelated t-tests. That is, where the responses in group 1 are independent of the responses in group 2. And completely randomized analysis of variance is simply an extension of that design. That is, where you have more than two levels of a single independent variable. You have more than two groups. We dealt with an example where there were 4 levels of a single independent variable. And we looked at the effects when we were looking at the hypothetical effects of exposure to violent television content on children's subsequent aggressive behavior. In the most general sense, analysis of variance separates all of the variance in scores into two components. One component is explained variance, that is, variance that can be attributed to the independent variable or the independent variables. And then what remains, obviously, is unexplained or error variance. That is, variance that is due to factors other than those being investigated. It is naive to suppose, for example, a one-factor model that explains 100% of the variance. It seems to me naive to suppose that exposure to various levels of violent content on television would explain 100% of the variance in children's subsequent aggressive behavior. It's likely that children's predisposition to behave aggressively is a function of a large number of factors, the way they've been socialized, perhaps their neurochemical makeup, perhaps their recent social or interpersonal or family history, a recent history with friends and so forth, all of which may affect the level of hostility or anger or aggression that they bring to the research environment. So it is, I was going to say likely, that there will be some amount of unexplained variance. It's universally the case that there is unexplained variance. The simplest causal model is that changes in A produce changes in some outcome. And we looked at an example of this, as I've indicated, that changes in the level of violent television content that a child views causes changes in that child's level of subsequent aggressiveness. In this instance, the explained variance would be variance due to A. And the unexplained variance would be variance due to all other factors. We also looked briefly at a more complex causal model, in which it's hypothesized that changes in this outcome variable are a function of two independent variables, or two treatment variables, A and B. In that circumstance, we observed that there are three sources of explained variance. There is variance due to A, there is variance due to B, and then there is variance due to the interaction between A and B. Interaction effects indicate, let me rephrase that, if the interaction effects are statistically significant, it indicates that the effects of one independent variable vary across levels of the other independent variable, so that what are called main effects become, for the most part, uninterpretable. That is, it's important to understand that these interaction effects are multiplicative. This is A times B. Interaction effects are not effects due to A plus B. Those effects, A plus B effects, are the combined main effects of A acting independent of B and B acting independent of A. An example of interaction effects. If you take some sorts of prescription drugs, you will experience some effect. If you drink alcohol, you will experience some range of effects. If you combine some types of prescription drug with alcohol, you will experience effects that are not experienced when using the drug by itself or using alcohol by itself. That is, the effects that occur are effects that occur only when those two factors act upon you in conjunction. So we can distinguish between main effects, that is the independent effects of A and the independent effects of B, and interaction effects, which are the multiplicative and unique outcomes experienced when A and B act upon you simultaneously. And when the interaction effects are statistically significant, first of all, and I'm simply reiterating here, that means that the effects of one independent variable vary across levels of the other independent variable. And second, it means normally that the main effects of those variables are uninterpretable. Are there any questions about this general model of analysis of variance? Hearing none, we consign this to whatever, some deep hole just outside Billings, Montana. Let's then work through another example of ANOVA. And this is sort of research situation that is common, certainly in mass media. Let's presume that we are hypothesizing that changes in A cause some changes in an outcome variable O. That is, changes, and A can be called the independent variable, the treatment variable, or the predictor variable. The outcome can be called the outcome or dependent variable. But this is a very simple causal model. Changes in A cause changes in some outcome. Let's presume that A is exposure to particular body images. And let's focus on print media. And what we would do is we would go and select certain types of print media, and we would identify examples of the body type, and clearly this sort of research focuses on the effects, typically focuses on the effects of a particular female body type on either male perceptions of women or on women's perceptions of themselves, or on the frequency with which women diet and so forth, or the extent to which they feel happy about their own body image. There's a lot, clearly there's a considerable volume of this sort of research that has accumulated over the last decade or decade and a half as issues of this kind have become more salient to us as a function of the increasing voice of women. Let us presume then that we have three levels of the independent variable A. We have A1, which is defined as low exposure to these body images. We have A2, which is defined as moderate exposure to these body images. And we have A3, which is high exposure to these body images. And in research, that those levels of exposures can be distinguished either experimentally by bringing participants into a research environment, a laboratory, and providing them either a small number of these images, a moderate number of these images, or a high number of these images. Or they can be distinguished by self-report, by asking persons how often they read certain magazines, or how familiar they are with certain sorts of advertisements. But let's not worry how we've distinguished between these three levels. We simply have participants who in one way or another, either through an experimental design or some naturalistic occurring set of circumstances, receive low, moderate or high exposure to specific sorts of female body image, particularly the body image that is presented to us routinely of the thin body image increasingly associated with what constitutes physical attractiveness or desirability or beauty in our culture. Let us presume further that the outcome is participants' happiness with their own body shape. And what we do is we focus on females between the age of 14 and 18. And these females are randomly distributed to the three conditions. Are there any questions at all at the moment about this research context? subsequent to their exposure, either through some naturally occurring process or through some experimental process, we measure the happiness with their own body shape of these, the female sample. We give them a questionnaire, let's assume, and the questionnaire, the scores on the questionnaire vary between 1 and 10, where 10 indicates I couldn't be happier with my own body shape, and 1 indicates I am so unhappy with my own body shape that I would rather be anybody else. I'd rather be from another planet, perhaps. I'd rather be another species. But high scores indicate high happiness and low scores indicate low happiness. Are we all following the little vignette that we're playing out here? Let's then focus on the output. Let's assume that the mean of group 1 is 7.2, that the mean of group 2 is 6.4, and that the mean of group 3 is 3.6. Clearly, females' happiness with their own body shape decays across levels of exposure. The issue is whether those differences are statistically significant. The null hypothesis, if you recall, in this case, would be that x bar 1 equals x bar 2 equals x bar 3. And in order to test that null hypothesis, we would conduct a completely randomized analysis of variance. Let us presume that there are 20 females in each group, so that the overall N is 60. Let us presume that alpha is 0.01. As we've seen before, an analysis of output, an analysis of variance output, first of all, separates the variance into its source. One source is between group variance, and the other source is within group variance. Let me ask you, which of these two is explained and which is unexplained variance? The between group variance is explained variance. We can explain the difference between 7.2, 6.4 and 3.6. Our explanation for those differences is that it accrues from different levels of exposure to a particular female body image. The within group variance is unexplained variance. If, for example, two persons in group 3 scored individually 5 and 2, we cannot explain that difference, because both of these participants were exposed to the same level or received the same level of exposure to a particular type of body image. They both received high exposure. So in a completely randomized analysis of variance, the between group variance is explained variance and the within-group variance is unexplained variance. The next column is headed, God, I hate being left-handed. Can somebody, pardon? Well, this is absurd. Did I not? Well, there we go. SS, not the German SS. This is sums of squares. Sums of squares. And let's presume that the between-group sums of squares is 40, and the within-group sums of squares is 80. The next column is headed DF, degrees of freedom. How many degrees of freedom are associated with the between-group term?
Number of groups minus 1.
The number of groups minus 1, which you would agree would be 3 minus 1, which is 2. Yes? What is the total degrees of freedom? The number of people in the study.
Sample size minus group.
I think you're answering the question that you want me to ask and not the question I did ask. Because you've got to the end product here. Because where I'm headed, obviously, is what are the degrees of freedom associated with the within-group term, and that is n minus k, where n is the number of people and k is the number of groups, which is 60 minus 3, which is 57. So that the total degrees of freedom are 59, which is the number of people in the study, uppercase n minus 1. Let me go back here a moment and make this just arithmetically easier. And now you're screaming because you say, why didn't you do this ahead of time? Because I now got to mess up my notes. Let's presume there are 114 degrees of freedom with the error term. The next column here is the mean square. And the mean square for each of these terms is computed by dividing the sums of squares by the degrees of freedom. So that the mean square associated with the between-group term is 20, and the mean square associated with the within-group term is 2. Yes? The mean square equals the sums of squares divided by the degrees of freedom. Yes. There are people looking at one another like, what happened there? What's going on? Where did we get this? Let me ask again. Are there any questions so far? Can you?
Where did the 114 come from?
I just made it up. I made it up. I changed it from 80 because I can't in my head divide 80 by 57. But I can divide 114 by 57. Yes.
What is SS again?
SS is sums of squares. SS is sums of squares. DF we know is degrees of freedom, and MS is mean square. Are there any other questions? Yes.
Where did the 2 come from? How do we deduce that?
Where did this 2 come from? The 2 here? I don't know. Where did it come from? It comes from, now they're believing me and they're rushing to my aid. The degrees of freedom associated with the between group term is given by k minus 1, where k is the number of levels of the independent variable, or the number of groups. In this case, 3. So that the degrees of freedom for the between group term is given by 3 minus 1, which is 2. The degrees of freedom for the error term, or the unexplained variance term, the within group term, is given by n minus k, where n is the number of people in the study and k is the number of levels of the independent variable. There are 60 people in the study. There are 3 levels of the independent variable, so that the within group degrees of freedom are given by then n minus k, which is 60 minus 3, which is 57. So that the total degrees of freedom in this case is 59, which is n minus 1. Right. I mean, if we do this just computationally, k minus 1 plus n minus k equals k minus 1 plus n minus k. The k's cancel one another out and you're left with n minus 1. Oui ou non? Oui? Oui for me too. I am not French, but I play one in the classroom. Are there any other questions? Analysis of variance relies then on an F statistic. This is simply the analog to Z or T. And F is computed by dividing the mean square for the between group term by the mean square for the within group term. That is, it's computed by dividing a measure of explained variance by a measure of unexplained variance. And in this case, would you agree, F equals 10? 20 divided by 2. The last column in an analysis of variance output is P. P indicates the probability of committing a type 1 error if you reject the null hypothesis. P indicates the likelihood of committing a type 1 error if you reject the null hypothesis. Let us presume that in this instance the P is 0.003. You understand, I hope, that evaluation of this null hypothesis involves a comparison between P and alpha. This is precisely the same as comparing a critical level of a test statistic with the observed or obtained value of that test statistic. This is not, the point I'm making is this is not some new trick. We're just doing the same trick, but in a different way. In this instance, would you A, reject the null hypothesis, or B, fail to reject the null hypothesis? All those who believe that, who would reject the null hypothesis. 1, 2, 3. All those who would fail to reject the null hypothesis. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 8 of you. 8 of you, I think that is. And the rest of you? Because there's more than 11 people in here. Not quite sure. If P, that is the probability of committing a type 1 error, is less than alpha, that is your willingness to commit a type 1 error, then you reject the null hypothesis. If P is greater than alpha, that is if the probability of committing a type 1 error is greater than your willingness to commit a type 1 error, you fail to reject the null hypothesis. So let me ask again. All those who believe that you should, in this instance, reject the null hypothesis. 1, 2, 3. 1, 2, 3, 4. A bunch, as they say down in this part of the country, a bunch. How many of you believe that you should fail to reject the null hypothesis? One lone sailor. How many aren't sure? At least one.
That's my question. What's that in alpha? It's hard to see on there.
For posterity, let me repeat your question and the answer. What's the alpha value? Because it's unclear there. The answer is 0.01. This is a simple matter of arithmetic. You were willing, if you set alpha equal to 0.01, you have said, I'm willing to take a 1 in 100 chance of committing a type 1 error. We could rephrase that as saying, I'm willing to take a 10 in 1,000 chance of committing a type 1 error. Would you agree? If P equals 0.003, the likelihood of committing a type 1 error if you reject the null hypothesis is 3 in 1,000. Is P less than alpha or is P greater than alpha? P is less than alpha. You were willing to take a 10 in 1,000 chance of committing a type 1 error. You're only being asked to take a 3 in 1,000 chance of committing a type 1 error. You reject the null hypothesis. You reject the null hypothesis. I have no better way of explaining this, but I'm quite willing to give it another shot if anybody is still unsure of this. In this instance, P is less than alpha. 0.003 is less than 0.01. You therefore reject the null hypothesis. You reject the statement that x bar 1 equals x bar 2 equals x bar 3. Do you understand it as well that this null hypothesis says that says that I, the independent variable, and O, the outcome variable, are independent of one another? Because if x bar 1 equals x bar 2 equals x bar 3, you would then, under those circumstances, you would fail to reject the null hypothesis. If x bar 1, x bar 2 and x bar 3 were absolutely equivalent, then clearly the independent variable, in this case level of exposure to a particular female body image, would have had no effect on the female's happiness with their own body shape. So the null hypothesis, which argues no difference between the groups, we can restate that as an argument that I, the treatment or independent variable, is independent of O, the outcome or dependent variable. We have rejected that statement. We have concluded instead that changes in A cause changes in O. That changes in level of exposure to a particular type of female body image influences, alters, changes females' perception, females' happiness with their own body image. Are there any questions? Yes.
I just don't understand how you got the value for P. Like, is that in an index somewhere?
I made it up. As I do so many things. In fact, I've made about 85% of what I've said in here up. I don't know anything about this stuff. I'm no better at it than you. I just sit in the seat where I can make it up. I made it up. It's a function of going to a table of F values and going across to that n column and looking at the proportion of all F values that are beyond this marker. The same way in which we used a t-table, the same way, well, more specifically, the very same way we used a z-table. This really is precisely the same. Setting alpha equal to 0.01 is precisely the same as determining some critical value of a test statistic, in this case F. P is the absolute equivalent of the obtained or observed value of that test statistic. If the underlying question here is, will we have to find this thing out on an exam? No. No. You will be given all of this information. Clearly, we've spent some time talking about how degrees of freedom are computed for the various terms And we've talked about how the mean square is determined for each of the terms, and we've talked about how f is computed for each of these terms. So you might be asked something about those issues. But will you have to decide a level of alpha? No. Will you have to decide the number of people in the study? No. Will you have to find a value of p? No. Will you have to compute the means of the various groups? No. You will be provided all of that information. And I'm not sure your motivation, obviously, I don't think your motivation was what's on the exam, but I just used it because I know it's floating around somewhere. It's floating around in my head. Are there any other questions? What you don't know at this point is why you've rejected this null hypothesis. You don't know whether you've rejected it because x bar 1 differs significantly from x bar 2, and or that x bar 1 differs significantly from x bar 3, and or that x bar 2 differs significantly from x bar 3. What you do know is that at least one of these comparisons produces a significant, statistically significant difference. What you now have to do is make each of these comparisons. That is, x bar 1 versus x bar 2, x bar 2, 1 versus x bar 3, and x bar 2 versus x bar 3. And to do that, you need some value from a comparison test, a between-group comparison test. And we talked about the use of one called Tukey's honestly significant difference test. That's trivial. You're not going to be asked on the exam, which of the following did we use? Tukey's honestly significant difference test, Bill Douglas's flip the coin in the air test. No. I just want you to understand two things. One, you need at this point to apply a between-group comparison test. And two, you have a number of choices in that regard. There are a lot of between-group comparison tests, and I just suggested one of those. Let's presume that the value, the critical value of that statistic is 2.4. That is, the comparison test value is 2.4. You're now back into a very simple game. You're comparing one group mean with another group mean. And you're comparing an observed difference between those two groups with a critical value of the statistic. Let me ask you, the difference between x bar 1 and x bar 2 is 7.2 minus 6.4, which is 0.8. The difference between x bar 1 and x bar 3 is 7.2 minus 3.6, which is 3.6. And the difference between x bar 2 and x bar 3 is 2.8. Is there anybody who's uncertain as to how we got to this point? Let me ask then, how many of you would conclude that females who received low exposure differed significantly from females who received moderate exposure to this specific female body image type in regard to their happiness with their own body shape? That is this difference of 0.8 statistically significant? It is not. That is, you do not, the null hypothesis here is that x bar 1 equals x bar 2. You fail to reject that null hypothesis. You conclude that there is no significant difference between the happiness with their own body image displayed by young females who have low exposure and young females who have high exposure to a particular female body, or moderate exposure rather, to a particular female body type. In the second comparison, the null hypothesis is that x bar 1 equals x bar 3. Do you reject or fail to reject this null hypothesis? What do we say? I hear voices from over here. Either I'm going deaf in my left ear, which is quite possible, or there aren't many voices over here. You'd fail to reject? Let me give you the answer, and we'll work our way backwards. You would reject the null hypothesis, because the observed difference between the groups exceeds one that will occur by chance. Yes?
How did you get the CP?
This critical test value, I made it up. Because you don't have to compute it. If you had to compute it, you'd invoke some formula, as you did with T and Z, and you compute it. But I'm assuming it's 2.4. That represents a difference that will occur by chance between the groups when chance is defined as alpha, that is 0.01. The observed difference exceeds a difference that will occur by chance. You therefore reject the null hypothesis and conclude that females who received low exposure to this particular body image are significantly happier with their own body shape than are young females who received high exposure. Yes? Let me stop. No, it's all right. I understand. For posterity, I've got revolution here. I've got chaos. I've got people asking one another. Are there any questions? Are there any questions you care to ask me? Perhaps I should rephrase it. Yes.
So where does the difference that we got, the 0.8 and 3.6 and 2.8, where does that come from again?
Where do these differences come from?
Yeah.
Simply from subtracting one group mean from another. That is, x bar 1 and x bar 2 involves 7.2 and 6.4. X bar 1 and x bar 3 involves 7.2 and 3.6. Are there any other questions you're willing to ask me? Yes? How do you get F? Okay, I'll circle back there right now. F is computed by dividing the explained variance by the unexplained variance. That is, dividing the mean square of the between group term by the mean square of the within group term. In this instance, that involves dividing 20 by 2. Okay? Is there anything else you're willing to ask me? Will Manchester United win the Premier League? Absolutely. Don't shake your head. You have an F in the class. You know, at least when you're in class, go along with the professor. Go, oh yeah. I think the difference between a student who's enrolled in a class and a student who has gone through the class and got a grade and gone on is that a student who's enrolled in the class, if they see you on campus, they will actually sprint 483 yards to ask you a question or just to say hi. A student who's been through your class, got the grade and has moved on will walk straight up to you and bump into you and won't even make eye contact. So, Manchester United okay, let's move on. The last step here is to evaluate the last null hypothesis, which is that x bar 2 equals x bar 3. This involves a comparison between 2.8, the observed difference, and the difference that will occur by chance. All those who believe we should reject this null hypothesis, I want it to be known to future generations that we all just stuck our hand up in the air. So if you're out there in future generations and you didn't know the answer to that question, I can't tell you how much trouble you're in. We would reject the null hypothesis. What we would conclude is that high exposure to this particular body image produces significant reduction in happiness with their own body image exhibited by young females. Because this group, X represented by X bar 3, differs significantly from the other two, which do not differ significantly from each other. Are there any questions? Yeah.
I feel stupid for asking this, but
no,
how
don't feel stupid.
Is it a numerical value that we associate to? I don't even know how to explain myself. How would we decipher that there is a significant difference or there isn't a significant difference? I don't understand that.
At the most, this is a two-step process, potentially a two-step process. The first is the evaluation of this primary null hypothesis that links together all of the groups, all of the levels of the independent variable. The test of that null hypothesis is an F-test. You compare P, the probability of committing a type 1 error, with alpha, your willingness to commit a type 1 error. And if P is less than alpha, you reject the null hypothesis, and then you have to go through this secondary process of comparing each mean with each other mean. If P is greater than alpha, you fail to reject the null hypothesis, and that's the end of the story. Presuming that you've rejected this overall null hypothesis, you now have to go through a process where you compare each group mean with each other group mean. And you do that by comparing the observed difference between the two groups with a difference that will occur by chance. This is precisely what we did in the context of z-testing and t-testing. And as I indicated in introduction to analysis of variance, it doesn't matter where you start. Ultimately, you get back to comparing one group mean with one other group mean. You will not be required to compute the critical value of this comparison test score. You will obviously be required to compute the between group mean differences, that is, the observed differences. And you will be required to make sense of the outcome. To recognize, that is, that what this pattern of results indicates is that x bar 3 differs significantly from x bar 1 and x bar 2, which do not differ significantly from one another. Therefore, the conclusion is that young women who received high exposure to this particular body image were significantly less happy with their own body image than were females who received either moderate or low exposure through the media to that body image. This is just going to require rehearsal. It's just going to require rehearsal. Okay. It's the process at the moment that is most important. This last step is just one piece of the puzzle. And even if you didn't master this by the time we got to exam 2, you're still going to do well on the exam, because most of the exam is over the rest of that stuff. But you should work toward understanding how you would translate what we found statistically into words. And the pattern of results here, as I've said, indicates that x bar 3 differs significantly from x bar 1 and x bar 2, but that x bar 1 and x bar 2 do not differ significantly from one another. That is, females who received high exposure to a particular female body image were significantly less happy with their own body image than were young females who received either moderate or low exposure to those images. Okay? Unless somebody is going to, bring me back for an encore, that's the end of the show.